I was just giving a student some advice about girls, but if you want me to make a video about that, just holla. Right now, I'm going to talk about exponential decay. So exponential decay is this process that happens whenever, now it's very interesting, there's always a decay rate. And if the decay rate, I'm going to call it R, if the decay rate depends on how many things there are at a given moment, then I could just put like, I don't know, a constant right there. If the decay rate depends on the number of things, then we're going to get exponential decay. And I could also have it depend on time in some interesting way. So there are a lot of ways to see exponential decay in physics, and I'll just throw a few of them at you. We're going to talk about radioactivity today, but I also see exponential decay in temperature change between two bodies that are coming to the same temperature, because the flow of heat depends on the difference in temperature. And as the difference in temperature gets smaller, the flow of heat gets smaller. So we'll see exponential decay there. Voltage on a capacitor, well, I guess the current depends on the voltage difference between the capacitor and the battery that you're charging it with. And as the capacitor charges up, it gets closer and closer. So we've seen exponential decay in voltage on a capacitor. The amplitude of an oscillator, if friction depends on how fast the thing's going, then the envelope of this oscillation is going to be an exponential decay. So there will be less and less friction when it's not going as fast. So this, in theory, if you put a mass on a spring, it takes forever to actually stop. In practice, you might be able to measure the oscillations in a cheap laboratory, like a high school physics laboratory for, I don't know, 20 minutes or something. But if you had very, very careful instrumentation, you might be able to measure it for many hours, many days, I don't know. Also, the intensity of light in an absorbing medium. Interestingly, that goes as a pseudo-exponential decay. There's some very interesting pseudo-exponentials in the atmosphere as well. And then as you're approaching terminal velocity, the closer you get to terminal velocity, the greater that frictional forces. So this is really similar to the amplitude of an oscillator. But we're going to go into this equation right here. I think this is the key equation for exponential decay in radioactivity. So let's jump into it. I'll give you the equation for exponential decay. It says n as a function of time, I'm not multiplying it by t, but I'm saying it's a function of time, is n naught, that's the number you started with, times the exponential, that's just e, the one you know and love, 2 point something something, and then there's this stuff up in that exponential. And let's label some of these guys. This is just the time spent decaying. I guess we're going to use seconds, which means, now an exponential can't have units inside of its argument. That's disgusting. If this is in seconds, then lambda has to be in inverse seconds. So this thing right here is called the decay constant. Do not confuse it with the decay rate. The decay constant is talking about how often decay happens, but it's not a rate. It is in inverse seconds, but we'll see how it's related to the rate in just a moment. This is the number of particles or rabbits that you started with. Number originally there. Okay, that was phrased kind of awkwardly. And this guy right here has to be the number later on. This is the number at time t. Number, oh, sorry, we're gone. Number, just kidding, number left at t, yeah, I'll just say the number left at time t. Okay, so what we want to do is first explore some of the terms that you hear in radioactivity. The one that I hear the earliest is that video game Half-Life. Does anybody know Half-Half? What? Dang it. Half-Life. Does anybody know what the symbol for that video game is? Interesting. Half-life is defined when, let me see if I can get a strict definition of half-life. I'm going to say that when the number at some time t equals t1/2, this is what I'm going to call the half-life. Half-life, that's my favorite symbol for half-life. The number left at time is the half-life, is half the original number. So that means that half of my original rabbits are dead, or half of the uranium-230 blah 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 has turned into something else. So only half of them are remaining, and we can do some simple algebra to find out what that time is and how it's related to this relationship right here. In particular, we're going to find out how it depends on the decay constant. Do you understand what this decay constant is doing? It's causing this function to start at some number. Let's just draw this function here. Here's time going on, and here's our number as a function of time. And this constant says that we're starting somewhere at n naught. And after some time, we're only going to have half as many. So here is 1/2 n naught. I'm going to say n naught divided by 2 is right there. And after some time, it will be there. After even more time, it'll be at n naught divided by 4. And that's that time right there. And I'm going to say that that probably takes twice as much time as it did to get to n naught over 2. So now I'll connect these dots and we'll see this interesting pattern of slow death here. But this is asymptotic here. It will never reach the axis. We will never run out of rabbits. Now, with rabbits, you really can count your rabbits, but if you have billions and billions of nuclei, that, that radioactive sample will, in principle, if you have an infinite number of nuclei, it will be radioactive forever. But its activity is decaying as a function of time. And so it's most dangerous when it's first formed. If you open that box, you order some radioactive material from Amazon. Do they sell radioactivity? I hope so. Check Amazon. That's as a mental note for me. Check Amazon for americium. Okay, I'll do that later. But we've got a number here, and so that means it is not asymptotic. It's asymptotic that direction. It is not asymptotic this direction. Do not confuse inverse graphs or hyperbole. Just kidding. Do not confuse graphs that look like this with decaying exponentials. It's asymptotic there, and it's asymptotic there. Now, you can't start with an infinite number of things. You have to start with some number originally there. That means when time is 0 right here, you're going to have n naught times e to the negative lambda times 0. Now, e to the negative lambda times 0 is just e to the 0. And e to the 0 is one of my favorite numbers, 1. E to the 0 is 1. Let's make another mental note of that. E to the 0 is 1, which means that the number when time equals 0 is the original number. That's sort of the definition of the original number, so maybe I'm wasting your time. My point is, just don't confuse this guy, which starts somewhere. That's a decaying exponential signature. It starts somewhere. With this guy that starts, well, I mean, it never gets there. This is not. This is an inverse graph. Something like y is 1 over x, etc. Those kinds of patterns for, what do you have those in? You have those in isotherms, and you have them in a lot of other places too. But exponential decay starts on the y-axis at a certain place. So let's derive the half-life. We had promised that we were going to do this. I'm going to take this fact and plug it into that equation right there, and I'm going to do it on the next page. Here we go. I'm saying that at the time of the half-life, I'm saying 1/2 n naught is the function that's on the right. I'm going to be using this function right here. I'm saying the number left at the half-life is the original number times e to the negative lambda times t 1/2. This defines the half-life. That's my plan to plug into this equation, and now I know everything. I'm assuming that I know the decay constant, so I'm just going to do a little bit of algebra. I'll note first that n naughts cancel out, and then I can take the natural log of both sides. I take the natural log of this side, I take the natural log of this side, and that gets rid of my exponential, because the natural log is the only thing that can kill an exponential. I have the natural log of 1/2, and that is the natural log of, e to the, oh man, no, that's all dead. It's all dead. And over here I get negative lambda t 1/2. That's the half-life. And the next step is to understand logarithms, I guess. Here we go. This is the natural log of 1 minus the natural log of 2. So that's kind of fun. And this is still negative lambda times t 1/2. And then I want to note that the natural log of 1, well, the natural log of 1 means that I'm taking e to the what is equal to 1. And of course, that question mark is 0. So 0 minus the natural log of 2 is negative lambda times the half-life. And if I finally solve for half-life here, I find that the half-life is equal to the natural log of 2 divided by lambda. Ding! Reflect on this for a moment. See lambda right here? Lambda is talking to us about how quickly decay is happening. It's our decay constant. So if lambda is big, decay is happening really, really quickly. That means that the half-life is going to be really, really what? If lambda is small, that means that the decay is happening really slowly. And that means that the half-life is going to be really what with lambda in the denominator if it's small? Okay, so that's something to understand, that this equation for half-life is useful. And also, I want to talk about why there's an exponential function. I really want to get at the heart of this idea. I'm saying that there's a decay rate. Like, here's what I want to say. This decay rate, aura, is called an activity. It could be called decay rate. I prefer to call it that. It could also be called activity. If you're working with a nuclear sample that is decaying, then, sorry, let me put an or in here so you're clear that it could be called either one of these things. If you're working with a sample that is radioactive, you want to know what its activity is. But its activity is its decay rate. So the faster that it is becoming non-dangerous also means the more dangerous it is at a given time. So that's kind of two sides of the same coin. It's a very interesting relationship. But decay rate is defined like this. Decay rate says, I want to know how many are decaying in some amount of time. All rates are over time, but this is just saying how often the number, how much the number of particles is changing, or rabbits in your basement, I don't know, whatever. And the cool thing about this is we're not interested in, of course it's going to be negative, right? Delta n will be negative. We're not interested in the minus sign for the decay rate. We're saying we want to know the change, and I just want the magnitude. But the interesting thing about it is that the decay depends on the number that are left. Does that make sense? If you've got 100 rabbits, then any given day you might have 10 rabbits die. Sure. But if you've only got 10 rabbits, they're not all gonna die in one day. You'll probably only have one die. If you've got 1,000,000 rabbits, maybe 100,000 will die the next day. I don't know. Feed the rabbits, for crying out loud. But if you say that the rate is proportional to the number that are left, all you have to do is you have to put a constant right there. And guess what? It's the freaking decay constant. It appears again here. I don't want that to surprise you. We're gonna see why it's in the other equation based on its presence in this equation. Right now, it's just a constant that tells us if a lot of rabbits are dying, the decay constant is big, and if it's very low chance of rabbits dying on any given day, then the decay constant is small. But of course, the decay rate, the number of rabbits dying every day, depends on how many rabbits you've got and what fraction of your rabbits are gonna die every day. You guys understand this? I hope you do. It's very important as we go on. I think this is probably the most important part of this lecture. So what I'm gonna say is that, first, let me be a little more honest with you. Decay rate is, in fact, the opposite of the change in number divided by the time, because we said change in number is negative, and I want the decay rate to be positive, so I'm just gonna flip that over. But you can kind of see then that delta n divided by delta t, now we're talking, this kind of looks like a little bit of calculus, is negative lambda times n. Interesting. Now I want to know what function satisfies this relationship right here. So I'm gonna lean in a little bit and say to you some sweet words about deltas. When I see a delta something over a delta something else, I'm thinking derivative. I'm thinking dn dt, and I am not a mathematician. You can check with a mathematician to see if they think this is okay, but my plan is to multiply both sides of this equation by dt and divide both sides of the equation by n. I will get the following equation. Watch this. Did you catch what I was gonna do? I'm gonna multiply both sides by dt, and I'm gonna divide both sides by n. And so n's cancel out on this side. Sorry, I should use a different ink when I'm canceling things. And dt cancels out on that side. And I find the following equation. dn divided by n is equal to, oh man, it's negative lambda times dt. And my favorite operation of them all is to integrate both sides of the equation. Algebra tells me that I can do whatever I want to both sides of the equation, and I'm going to integrate both sides of them. This is a cool function when you integrate it, isn't it now? Well, this is a really wonderful equation. When I integrate negative lambda over t, do you think that I'll get anything interesting coming out there? How does negative lambda depend on t? Well, let's check lambda. It's a freaking constant! See the word constant right there? Great. Here's my plan. I've got this equation, and I look at the right side first. Negative is constant, lambda is constant, and I have negative lambda times the integral over dt. I'm probably just gonna get a time there. And then over here, what do you want, some constant? Yeah, I'll put a constant there. Here's another constant for you. Okay, and then on this side, I get the natural log of the number. Now that's a beautiful thing. Let me present it to you like this. Here's the natural log of n, and here's this integral over t. We probably should go one more line before we start talking. Natural log of n is negative lambda times t plus some stupid constant. And my plan is now to exponentiate both sides. I'm going to raise each of the sides as a power of e, and e to the natural log of n is simply n. Now we've got n, and incidentally, it's as a function of t, right? You see t on the other side. I've got e to the negative lambda t plus c, which is e to the negative lambda t times e to the c. And all I have to do now is investigate t equals 0. See, mathematicians don't get to do this final step because they don't know boundary conditions, but the physicist can take the boundary conditions and they can say at t equals 0, the number has to be, like this is the definition. The number as a function of t when t equals 0 is n naught. So that's my plan. I'm going to plug in 0 to this equation, and I find that n of t equals 0 is, by this equation, it's just going to be e to the negative lambda times 0 times e to the c. And that is simply e to the c. So what if I define, by this definition right here, I can define that n t equals 0, right? I can define that to be n naught. And now I take this equation. Ready? I'm taking this equation right here. I've taken this guy, and I'm plugging in that e to the c is n naught. And I'm going to find that I have finally proven that equation that I just threw at you earlier. The number of particles or rabbits left as a function of time is n naught times e to the minus lambda times t. That is pretty much all I have to say about that. Oh wait, I can say some more about rate now. Wait, here's rate. Rate is the derivative of the number that are left. So we can take this equation, let's take this one more time. I'm saying the number as a function of time is n naught times e to the minus lambda over t, and where I previously had rate defined as, what did I say? Rate was delta n over delta t, absolute value, blah, blah, blah. Now I'm going to define rate as dn dt. So it's the slope of the graph that we had at the beginning. Oh, initially, this graph is very negatively sloped. Remember, it's the opposite of the slope, right? It's the opposite of the slope. So right now we've got a big decay rate, and now we've got a small decay rate, and now it's even smaller. But at the same time, it also depends on the number that are left. So let's look more at this decay rate. I want to look a little bit more at this decay rate right here. And the decay rate is, what? The decay rate? Let's look at this decay rate. I'm supposed to take the derivative of that function right there with respect to time. R is d dt of n naught e to the minus lambda t. And I like differentiating exponentials. It's a very fun thing to do. We'll pull out n naught, and then we'll say we get a negative lambda times, Oh my goodness, we get a negative lambda times that exponential. I just get e to the negative lambda times t. And what I can say now is that, wait, we didn't want this to be positive, right? We're supposed to put a minus sign out front here. Here's a minus sign, and then I'm supposed to multiply by that right there, and these guys are supposed to cancel out so that I get positive, positive, positive. And I find that the rate is lambda times m naught. Wait a second, times e to the minus lambda t. So the rate, the activity is even decaying, but what if I want to know the rate initially? This would be the rate at t equals 0. That's gonna be negative, oh sorry, not negative. I'm gonna just plug in 0 to this equation right here. It is simply lambda times n naught times e to the 0, which is 1. So the initial rate is lambda times n. In fact, well, I'll just leave it right there. That's all I have to say about that. And I could also have it depend on time in some interesting way. So there are a lot of ways to see exponential decay in physics, and I'll just throw a few of them at you. We're going to talk about radioactivity today, but I also see exponential decay in temperature change between two bodies that are coming to the same temperature, because the flow of heat depends on the difference in temperature. And as the difference in temperature gets smaller, the flow of heat gets smaller. So we'll see exponential decay there. Voltage on a capacitor, well, I guess the current depends on the voltage difference between the capacitor and the battery that you're charging it with. And as the capacitor charges up, it gets closer and closer. So we've seen exponential decay in voltage on a capacitor. The amplitude of an oscillator, if friction depends on how fast the thing's going, then the envelope of this oscillation is going to be an exponential decay. So there will be less and less friction when it's not going as fast. So this, in theory, if you put a mass on a spring, it takes forever to actually stop. In practice, you might be able to measure the oscillations in a cheap laboratory, like a high school physics laboratory for, I don't know, 20 minutes or something. But if you had very, very careful instrumentation, you might be able to measure it for exponential decay. It says n as a function of time, I'm not multiplying it by t, but I'm saying it's a function of time, is n naught, that's the number you started with, times the exponential, that's just e, the one you know and love, 2 point something something, and then there's this stuff up in that exponential. And let's label some of these guys. This is just the time spent decaying. I guess we're going to use seconds, which means now an exponential. I was just giving a student some advice about girls, but if you want me to make a video about that, just holla. Right now, I'm going to talk about exponential decay. So exponential decay is this process that happens whenever, now it's very interesting, there's always a decay rate. And if the decay rate, I'm going to call it R, if the decay rate depends on how many things there are at a given moment, then I could just put like, I don't know, a constant right there. If the decay rate depends on the number of things, then we're going to get exponential decay. Many hours, many days, I don't know. Also, the intensity of light in an absorbing medium. Interestingly, that goes as a pseudo-exponential decay. There's some very interesting pseudo-exponentials in the atmosphere as well. And then as you're approaching terminal velocity, the closer you get to terminal velocity, the greater that frictional force is. So this is really similar to the amplitude of an oscillator. But we're going to go into this equation right here. I think this is the key equation for exponential decay in radioactivity. So let's jump into it. I'll give you the equation for